Hi, this is Mrs. Boland with University of West Florida, Elements of Statistics, Hypothesis Testing, which is Mod 8 for our course. I'm doing Lecture 3, which is the closing lecture. Very important concepts. The concepts in this lecture will, without a doubt, be reflected on our final exam as well as our next exam coming up. So please make sure that you pay attention, that you do the exercises in here when you're given an opportunity, and that you do all the homework that has been assigned to make sure that you are strong with this concept prior to our exam. Okay, so let's go ahead and get started. The first thing we're going to be doing is we're going to be talking about hypothesis testing when it comes to the difference between two means or two proportions. And the first concept is going to be independent samples. So in this section, we are assuming that we have independent data and would like to test for differences between two different populations. So testing the differences between population 1 and population 2 mean. It's the first thing we're going to be talking about when sigma 1 and sigma 2 are both known. Now we're going to rewrite our hypothesis a little differently than what we've been doing, because we're now interested in a difference between two groups. So think about it like this. I want to test the effectiveness of maybe flea control on dogs versus cats. So the mu1, population 1 could be represented by the dogs, population 2 could be the cats. Or maybe I want to take and see the heartworm effectiveness of a product comparing a small breed to a large breed. Maybe I think that the effectiveness when it comes to the terrier breed with dogs is different compared to, let's say, Great Pyrenees and other large breeds. So those would be examples of when we might want to compare the effectiveness of something comparing to two different populations. And remember, these are independent, and we'll go over dependent in just a few minutes, but what we're talking about right now are independent samples and independent populations. So recall that we always use an equal sign in our null hypothesis, or just the opposite of the alternative. So our null hypothesis would be mu1 subtract mu2 equals 0, okay? We could write it like that, or we can apply some simple algebra and add mu2 to both sides and come up with mu1 is equal to mu2, okay? So whether the difference between the two is 0 or whether we state they're equal, both of these say the exact same thing. So make sure you think about that so you realize that. So let's look at different types of alternative hypothesis. We have our left tail test, which would be that mu1 minus mu2, remember it points left, is less than 0, or I could write it as mu1 is less than mu2, again following simple algebra. I could have a right tail test, which is that mu1 minus mu2 is greater than 0, again pointing to the right, meaning it's a right tail test. Or if I added mu2 to this side, it becomes this right here, that mu1 is indeed greater than mu2. And then I have my two-tailed test, which simply says they're not equal, okay? Written as mu1 minus mu2 does not equal 0, or that mu1 does not equal mu2. Remember, all 6 of these statements, okay, these two right here, these two right here, and these two right here, all mean the exact same thing. So I have 3 different hypotheses right here, written, each one of the 3 written in 2 different ways, but all saying the exact same thing. Now we have a new test statistic, and because we have our population standard deviation known, we're going to be doing a z-test, and we're going to be looking at the difference between our samples, and we're going to subtract the difference between our population expected, or our population mean, and then divide it by sigma 1 squared, which is also known as the variance for population 1, divided by the sample size for population 1, plus the standard deviation for sample, the second sample squared, again that's called the variance of the second population, divided by the sample size for the second population, all of that underneath the radical, okay? Because in this particular course, we are going to always have this number right here equal to 0, where we're comparing it to 0. This will fall out, so a simplified version of it looks like this, okay? You'll still see me write this, okay? Because it's an old habit, it's a good habit. It's old habits die hard, as they say, but it's a good habit. So I'm going to keep writing my -0, because at some point we're going to, I'm sure there's a statistician somewhere listening to this, future statistician, and you're going to need to remember that 0 is not always what the difference is. Sometimes it's 2, maybe it's -2, maybe it's 10, maybe it's thousands of dollars, where you think one sales technique increases the sales by thousands of dollars versus another sales technique. So it's not always going to be that we're looking for 0, okay? So I will keep using this formula right here. So just kind of keep an eye out, and this is the one we're going to be using. And then remember that all of our hypothesis steps are the same: hypothesis, test, p-value, critical, rejection, conclusion, interpretation type thing, okay? So here we go. So a consumer group is testing camp stoves. To test the heating capacity of the stove, it measures the time required to bring 2 quarts of water from 50 degrees Fahrenheit to boiling. So we have a study that we're doing, and we've got it defined. It's exactly 2 quarts of water. We're starting at this temperature. We're going to boiling at sea level. Okay, so we have an experiment that can be replicated, duplicated, repeated without any changes and consistently. So 2 competitive models of camp stoves are under consideration. We have 10 stoves of the first model and then 12 stoves of the second model. So our sample sizes are different. We have 10 stoves of one model, 12 stoves of a different model. And it says the following results were the same, and they give us summary statistics. Out of Model 1, X bar is 11.4 minutes with our population standard deviation 2.5, and we sampled 10. Model 2, it took on average 9.9 minutes to get to a boil with a standard deviation of 3, and we sampled 12. It says assume the time required to bring the water to boil is normally distributed, very important, for each stove. Is there any difference, okay, either way, between the performance of these 2 models? Use a 5% level of significance. So here we go. So the first thing I want to do is make sure that we write down our hypothesis test correct, okay? So our alternative hypothesis, H naught, is we're looking for a difference, so it's going to be a 2-tailed test. So we have H1, so it's going to be mu1 equals mu2. And my computer is really hot. It's been working all day long on these videos, and it's having a hard time keeping small things. So hopefully this will work out for me, so that they're not equal. And then this right here, I can switch to an eraser. So we have H1 is mu1 is equal to, not equal rather, to mu2, and H naught is mu1 does equal mu2. So that's where we're going to get set up. We have our summary statistics right here, and what I want to make sure I write down that it's in the front of my mind is that alpha is equal to 0.05. So I have my population standard deviation, so this is step 1. Step 2 says I'm on a Z distribution. Step 3, I need to identify my critical value, and so it's a 2-tailed test, so that's going to be 0.025 in the tail. So I'm going to come down here and I'm going to pull up my tables. So here's my tables. I'm going to look up 0.025, 0.025 right here. So it's negative 1.96 is what it's going to be. You come up here. So it's negative 1.96. So Z is going to equal plus and minus 1.96. Because it's a 2-tailed test, I have a plus and a minus. So now I'm going to draw my picture. Step 4. We're going to put 0 in the center. We're going to put negative 1.96 to the left, positive 1.96 to the right. I know that in here, half of alpha, which is going to be 0.025, and 0.025 over here, and this is my rejection region. And then in the center, this is my fail to reject. And I put in here 0.95. So 0.025 plus 0.95 plus 0.025 equals 1.0. And now I have my picture drawn and labeled properly. So we can go ahead and we can highlight this right in here. And then we can go ahead and highlight our rejection areas right in there. Now the test statistic is a little tricky, so I'm going to cut and paste it in real quick so we have that right in here for step number 5. Okay, so step number 5 is we're going to calculate our test statistic. So step 5, and it's going to be equal to, it's going to be x bar 1 minus x bar 2. So I'm going to come up here. X bar 1 is 11.04 minus 9.9. So 11.4 minus 9.9. That difference minus mu1 minus mu2, which is 0, divided by the square root of the population standard deviation squared, aka the variance. So it's going to be 2.5 squared. 2.5 squared divided by my sample size, which was 10, plus my population standard deviation, which is 3.0, divided by my standard, or my other, which sample size was 3.0 squared, divided by 12, all underneath the radical. And so we're going to grab our calculator and put this in. And let me see if I can get my calculator to stay right. There we go. So we're going to turn it on here, clear it out. Make sure you overuse parentheses. So because this is 0, I really don't need it here, but I put it there because it's important for you to remember that it is always there. So it's 11.4 subtract 9.9. Close your parentheses, okay? Divide. Now, all of this is going to be underneath your radical, and your radical can count as a parenthesis, so you're okay on that. But you need to have this right here set in parentheses and this right here set in parentheses, okay? So underneath the radical right here, I'm going to open up another set of parentheses. So it looks like this, okay? And I'm going to go 2.5 squared. And then I'm going to go divide 10, close parentheses, plus, open parentheses, 3.0, I don't have to do the 0.0, squared, divide 12, close parentheses. Now I come out from underneath the radical and I hit enter. And I end up with 1.279. So since the z tables are to two values, I'm going to only go to two decimal places on my test statistic. So it's 1.28. So 1.28 is my test statistic. So 1.28. Now I'm going to plot it on here. It's a positive value, so it's going to be between 0 and 1.96. So right here I'm going to put 1.28. So I have it plotted right here, and you can see that I'm in my fail to reject. Part 6 is your conclusion, and I'm going to fail to reject H naught at alpha equal to 0.05. Now I want to state my p-value. We've only done a p-value with a two-tail rejection one other time, so I want to show you again how to make sure you know how to do your p-value. Okay, so you can say my p-value is equal to, are you ready? So it's 1.28. So we have to come into the tables. It's a two-tailed test. So we're going to come over to negative 1.28. So negative 1.28. So it's all the way over here, okay? Because the last one is a 9, so the second to last is the 8. So 1.28. So this is the area under the curve to the left, or to the left of negative 1.28. It's symmetrical, so this is the same as if it was to the right. So it's 0.1003. So 1.1003. So in this area, it's a two-tailed test. So my p-value is equal to 2 times 0.1003, which is going to be equal to 0.2006, because this area over here, and then if we had a negative 1.28, we have to double it because it's a two-tailed test, and we'd have to look at the area in here. I'm going to highlight it in yellow so you can kind of see. This is the area that we're looking at, and we're going to add it together to get our p-test, or p-value rather. Okay, and our p-value, you can see, is huge. It's 0.2006. So we definitely fail to reject H0, and we can conclude that there is no difference between how long it takes for these two different camp stoves to get to a boil, or to boil water. Okay, so not a significant difference in time, so definitely buy the less expensive model in my opinion. Okay, let's look at another one. This one here, it says a teacher wishes to compare the effectiveness of two teaching methods to her students. The students are randomly divided into two groups. The first group is taught method 1. The second group is method 2. At the end of the course, a comprehensive exam is given to all students. The first group consisted of 49 students, and they had a mean score of 74.8 points. The second group had a sample of 50 students in it with a mean score of 81.3 points. Earlier research for the two methods indicated that sigma for population 1, method 1, is 14, and the standard deviation for the population 2 is 15 points. The teacher claims that the second method will increase the mean score on comprehensive exams. Is this claim justified at the 5% level? Okay, so we're asked to test the teacher's claim that the second method, okay, the teacher claims that the second method will increase the mean score on the comprehensive exam. So an easier way sometimes to look at this is to say, okay, mu1 minus mu2 equals 0. I got that part, okay? Let's look at the alternate hypothesis. What should this be? Mu1 minus mu2 equals what? Okay, less than 0, greater than 0, or not equal to 0. Well, it says that if the teacher claims that the second method will increase the mean score, that means I'm expecting mu2 to be a larger value than mu1. So if I take a smaller value and subtract a bigger value, so let's just put an example. If I have 3 and I subtract 5, it equals -2, which is less than 0. So in order to test this teacher's claim, I'm going to say that it's mu1 minus mu2 is less than 0, okay? Because what I'm saying is the second method is giving me higher scores than the first method. So you can take any number that's smaller on the first, bigger on the second, subtract it, and you're going to see you get a negative number, which is less than 0. So this becomes less than 0. Or I could have said that this would then be, if I added mu2 to both sides, I would get mu1 is less than mu2. Either one of these statements right here is accurate, and that's what we're testing, okay? So that is step number 1. Step number 2, what is our distribution that we're using? Well, we've been given the population standard deviation for both populations, so we are on the Z distribution. Okay, step 3 is our critical value. Step 3 is our critical value. We are at a 5% alpha level. And you can see we are a one-tailed test. It's a left-tailed test. So our Z value is going to be negative. So Z star is going to be negative, and I'm going to have 5% or 0.05 in the left tail. So let's go ahead and look up 0.05 on our table here. So 0.05 is going to be right here between these two values of negative 1.645. So we're going to use negative 1.65. So negative 1.65. Part 4 is, let's go ahead and draw a picture of our scenario. Okay, let's put in our fail to reject as well as our rejection region. Okay, oops, and let's see, yep, it's a left tail test. So we're going to have a negative 1.65 right here. Fail to reject. And then right in here, we're going to put all of alpha 0.05 because it's a one-tailed test, and this is where we reject. Okay, and then what we're going to do is we're going to highlight this green because this is our fail to reject. Okay, we didn't find any significant statistical difference if we fall in here. However, if we fall in here, we do find a significant statistical difference. Okay, so step 5, we need to find our test statistic, which is Z. So Z is going to be equal to X bar 1 minus X bar 2. So X bar 1 is 78 or 74.8, and X bar 2 is 81.3. So 74.8 minus 81. So 74.8 minus 81.3, 81.3. That's the difference right there. Subtract the difference of the population mean, which is 0. Divide it by the square root. Okay, standard deviation for population 1, 14, and sample size is 49. So it's 14 squared divided by 49 plus standard deviation for population 2 is 15 divided by 50. So it's 15 squared divided by 50, and all underneath the radical. Okay, we're going to throw this in our calculator, and it's going to look like this when we do. Again, I want to show you how to make sure that everybody's doing this right. Calculator errors are a big cause of some of the challenges we have on these exams, and then with us doing them online, it can create a little bit more of a challenge. So make sure you show all work possible, and I am going to be asking you to email me your work after your exam. So it's 74.8 minus 81.3 minus 0 is just going to be 0, so it's going to be divided by the square root, parentheses, 14 squared divided by 49, close parentheses, plus open parentheses. I want to show you something else here, guys. 15, and if you use this technique right here, see right here I have just a square button, but if I decide to go raise to the power of 2, notice that my cursor is still up high, so I have to hit this button to bring it back down if I use this. If I use just this button right here, I don't have to do that, okay? So then divide through by 50, close parentheses, come out from underneath the radical and hit enter. I get negative 2.229, so I'm going to make this a negative 2.23. So negative 2.23. Negative 2.23. So now we can plot our test statistic of negative 2.23 right over here. We get negative 2.23, and you can see that we are indeed in the rejection region. So we will then go ahead and conclude that we will reject H naught and conclude the alternative. So since negative 2.23, which is the test statistic, is less than negative 1.65, I will reject H naught at alpha equals 0.05 and conclude that method 2 will result in higher test scores. My p-value equals, let's go see what that equals. So it's negative 2.23 one-tailed test. So all I have to do is look up negative 2.23, so this is 0, 1, 2, 3, so it's 0.0129 is equal to 0.0129. Okay, and as you can see, the p-value is less than my alpha value. Just another way of making sure that we have everything done correctly. Alrighty, let's look at our next problem. Testing when the difference between mu1 and mu2 when sigma 1 and sigma 2 are both unknown. So just like in the one sample test, we can test the difference of means when we do not know the population variance or standard deviation. Instead of z, we're going to turn to the t, and our test statistic becomes this right here, which, as you can recognize, is very similar to what we've been doing, except for we have sample standard deviation, and we're going to let it be a t statistic, and our degrees of freedom is the smaller of the two, n minus 1 and minus 2. So you're going to use the degrees of freedom for the smaller sample size. Is what you're going to do. Alrighty, so let's go ahead and put this into application. So we have two competing headache remedies claimed to give fast-acting result or relief. An experiment was performed to compare the mean length of time, so the mean length of time required for bodily absorption of brand A and brand B headache remedies. 12 people were randomly selected and given an oral dosage of brand A. Another 12 were randomly selected and given an equal dosage of brand B. The length of time in minutes for the drugs to reach a specific level in the blood was recorded. The mean, standard deviation, and sizes of the two samples are as follows. So at brand A, X bar is equal to 21.8 minutes. Standard deviation is 8.7, sample size 12. Brand B, X bar is 18.9 minutes. Standard deviation is 7.5 minutes, and our sample size was 12. So just a quick cursory overview is that B was faster on the X bar, and it also yielded a smaller standard deviation, tighter standard deviation, which is interesting to observe. So past experience with the drug composition of the two remedies permits researchers to assume that both distributions are approximately normal. Let us use a 5% level of significance to test the claim that there is no difference between two brands in the mean time required for bodily absorption. Okay, so what we're going to have is we have H naught, H1, and that we're going to be testing that there is a difference is what we're going to be testing. So mu1, mu2 are not equal versus they are equal. So that is step one. Step two is we're going to identify the distribution. Well, because we have the sample standard deviation of both populations, we are going to be using the t distribution. Step 3 says find the critical value. Well, we're going to have a positive and negative, and it's going to be a t. So it's going to be t is equal to positive and negative some value. It's going to be t at 0.05 for a two-tailed test, and the degrees of freedom is going to be 11 because both are the same size, so it's just 11. So we're going to come over here to the t-test. So we have a two-tailed test. So we're going to be looking right here at two-tailed test, alpha equal 0.05, and then we're going to be having 11 degrees of freedom. So two-tailed test, 0.05, 11 degrees of freedom. 2.201 is going to be our critical value. 2.201. 2.201. Step 4, we're going to draw a picture. So of our put 0 in the center. It's a two-tailed test, so negative 2.201, positive 2.201, failed to reject, reject at 0.025 right in here, and reject at 0.025 right in here. And we can highlight right in here just real quick. This is the fail to reject area. And then we have our reject right here and right there. Okay, the next thing we need to do is step 5, which is our test statistic. And our t is going to equal, it's going to be 21.8 minus 18.9 minus 0 divided by the square root of 8.7 squared divided by 12 plus 7.5 squared divided by 12. And we're going to put that in our calculator and we shall find out. Let's see here. Turn our calculator on, clear it out, and we're going to start with the parentheses to capture the numerator. So 21.8 minus 18.9, close parentheses, divided by square root, and then we're going to open parentheses. It's going to be 8.7 squared divided by 12, close parentheses, plus open parentheses, 7.5 squared divided by 12, close parentheses, come out, and hit enter. And that is 0.874, so we'll just put 0.87 is our test statistic. So 0.87, and we'll plot this right over here at 0.87, and you can clearly see that we failed to reject the null hypothesis. So we fail to reject H naught at alpha equals 0.05. Okay, so there you have it. Let's look at our next problem. Okay, so we have another problem here working off of a similar concept as what we just had. So the difference between this one and the prior example is the sample size and what we're actually studying. So this one here, it says that we're claiming that B claims to be faster, and I'm assuming in relieving headaches. And our sample sizes have changed as well as our X bars. So it says brand B claims to be faster, so let's test that at a 5% significant level. So if brand B claims to be faster, that's going to be mu sub 2. So, and we're going to test this claim. So that's going to mean that mu1 value, if we're looking at time, is going to be greater than mu2. Because if you're faster, your time is shorter. Okay? So if we have a stopwatch and we're saying who can run a quarter mile faster, and we click the stopwatch and two people start to run, the person who crosses the finish line first ran faster and has a smaller time numeric value. So if we say that brand B is faster than brand A, that means mu2 is going to be smaller than mu1. Okay? So you have to look at what are we actually talking about and testing. So we're just going to say up here that these are equal. So that's step 1. Step 2 is what distribution? We're going to be on the t distribution because I have sample standard deviations for both populations. And then 3 is what is my critical value? My critical value is going to be t star, and we're going at a 0.05, and then the smaller of the two, which is 8, so it's going to be 7 because n minus 1 is going to be 7, and we are one sided test, a right tail. So we have a one tail test, alpha equals 0.05, and our degrees of freedom is 7. So right here is our critical value. Right here actually, degrees of 7, so it's right here under one tail 0.05, so it's 1.895. So now we want to take and draw a picture of what's being represented. So our standard normal curve, mu in the center. It's a right tail test, 1.895. Here's our fail to reject. And then over here, we're going to put alpha right in here, which is 0.05. And this is where we going to reject. So now we can go ahead and add a little bit of color in just to make sure everybody is on the same page here. This is where we're going to fail to reject. And then over here is our rejection area. So now we need to come up with our test statistics. So this was 0.4 and this is 0.5. So t is going to equal x bar 1, which is 20.1 minus x bar 2, 11.2, subtract 0, divided by the square root of 8.7 squared divided by 12 plus 7.5 squared divided by 8, and throw this on our calculators and we will find that it is equal to 2.44. So if we plot that over here, we're going to find out 2.44 is right in here in the rejection area, so that we can stay then on step 6 that we will reject H naught and conclude H sub 1, the alternative. So let me type that up for you and I'll be right back. Okay, so here is my conclusion. Since 2.4 is greater than 1.895, that would be the test statistic is greater than the critical value, I will reject the null hypothesis that alpha equals 0.05 and conclude that the medicine brand B works faster than brand A. My p-value is between 0.025 and 0.01. Again, that is found by coming over here at 7 degrees of freedom and finding where is 2.44 found. And 2.44 is between these two values. 2.44 is greater than 2.365, but less than 2.98. So I come up here, and one-tailed test, it is between 0.025 and 0.01. Okay, now we're looking at testing with proportions. Suppose we have two independent binomial experiments. We will now discuss testing the difference between the proportions. Our test statistic is as follows. We are missing part of that right here. Let me go grab and insert part of this because you need to know how to calculate P bar and Q bar. Okay, so I brought up your formula sheet real quick, and here is your formula sheet for hypothesis testing, difference of proportions, and the test statistic here. It's written a little bit different than what is presented right here, okay? It's the same, the results are the same, it's just a different way of calculating. You know, algebra, you can do lots of different things. But what we didn't have right here is the P bar. So let me go ahead and grab that right now, where we can say that P bar. So here's our test statistic, and you can see it involves P bar and Q bar, and P bar is calculated like such. Q bar is just simply 1 minus P bar. Okay, so Q bar is just 1 minus P bar. So there's our test statistic. Everything else is the same. County clerk wishes to improve voter registration. One method under consideration is to consider reminders in the mail to all citizens in the county who are eligible to register. As part of a pilot study to determine if this method will actually improve voter registration, a random sample of 1,250 potential voters was taken. Then this sample was randomly divided into two groups. So we took 1,250 people, divided into two groups. So there were 625 people in group 1 and 625 in group 2. For group 1, no reminders to register were sent to them, and the number of potential voters from this group who registered was 295. Group 2, this group had reminders sent in the mail, and the number who registered was 350. So 55 more people. The county clerk claims that the proportion of people who registered was significantly greater in group 2. On the basis of this claim, the clerk recommends that the project be funded for the entire population of the county. Use a 5% level of significance to test the claim that the proportion of potential voters who registered was greater in group 2 and group 2 that received the reminders. So here's our definitions, here's our sample sizes, here's our excess, okay? And this was our total number of people that we looked at. So step 1, we're going to write down our null hypothesis, which is that the proportion for population 1 equals the proportion of population 2, and our alternative is that the proportion for population 2 is larger than 1, greater in 2. Okay? Step 2, what distribution? We are doing proportion, so therefore it will be a z distribution. Step 3 is our critical value. We're going to look for z star. It is a one-tailed test to the left, and so we know it will be a negative value. Alpha is equal to 0.05. Alpha equals 0.05. So 0.05 in the left-hand tail will give us a critical value. 0.05 will give us a negative 1.65. Negative 1.645, but we'll round it to negative 1.65. So that will be our critical value, negative 1.65. Step 4, draw a picture that represents our situation here. Okay, always draw your picture, remember that. It's a left-tailed test, so my z is going to be over here at negative 1.65. And here is where I fail to reject. In here, I put my alpha 0.05, and I'm going to reject in here. So step 5, I need to take and determine what p hat 1 is, and then also p hat 2. So coming up here, I had for group 1, 295 people that registered to vote out of 625. So p hat 1 is 295 divided by 625. And then p hat 2, how many people registered to vote? 350 out of 625. So 350 registered out of 625 that were mailed reminders. And throw those in your calculators. And we're going to find out that 295 divided by 625 is equal to 0.472. And then 350 divided by 625 is equal to 56.56. Alrighty, the next thing I need to calculate is P bar and Q bar. So P bar, let me move that down just a touch. P bar is going to be equal to, it's the average response. So it's x sub 1 plus x sub 2 divided by n sub 1 plus n sub 2. So we had 1,200 people total, but I'll show it to you separately. So it's x sub 1 or no, it's x sub 1 plus x sub 2 divided by n sub 1 plus n sub 2. So x sub 1 is 295 plus x sub 2, 350, divided by 625 plus 625, which is the 1250. So now we're going to add together 295 plus 350, make that a 50, and we get 645 divided by 1250, and that becomes 0.516. That's P bar. Q bar is equal to 1 minus P bar, which is 1 minus 0.516. Which is 0.484. Okay, I think we have all the numbers we need now to calculate our test statistic. So our test statistic, if we come back up here, is going to be P hat 1 minus P hat 2. That's the easy part. Then it's going to be P bar times Q bar divided by N on both sides, all underneath the radical. So it's going to look like this. Z is going to equal to P hat 1 minus P hat 2 divided by the square root of P bar Q bar divided by N1 plus P bar Q bar divided by N2 underneath the radical. I'll double check that real quick. Yep. Okay, and here we go. So to substitute all these values in, P bar 1 is right here at 0.472. So it's 0.472 minus 0.56 for P hat 2 divided by the square root of P bar 1, which is 0.516 times Q bar, 0.484 divided by N1, which was 625, plus P bar again, So 0.1516 times 0.484 q-bar divided by sample size for sample 2. And all of that looks like that. Okay, so I'm going to show you how to put this in your calculator, because this has potential for errors here to pop up. So we'll bring our calculator over here real quick. Turn it on, clear it out. Parentheses, 0.4472 minus 0.56, close parentheses, divide, square root, got it. Now we're going to put in parentheses, 0.516 times 0.484 divide 625, close parentheses, plus parentheses 0.516 times 0.484 divide 625, close parentheses, come out and hit enter. Negative 3.11. So negative 3.11. So negative 3.11 is our test statistic. So now we come up here, negative 3.11, negative 3.11, right over here, and we are going to reject. So in this case, we are going to, let's see here. Okay, so the last thing we need to do is be able to determine the sample size when we're estimating our population proportion, okay? So if we're given a confidence level in the value of P and Q, the sample size that will produce a predetermined maximum error, E, of the confidence interval estimate of our proportion is equal to N equals Z squared PQ divided by E squared. Okay, so very similar to what we just did for estimating the sample size for our mean. Now we're going to be estimating the sample size necessary to meet certain requirements of our proportion. So I'm going to scroll up. Here's our formula that we need to stay focused on. And let me go ahead and bring up the tables down here. Here's our sample size, minimum sample size to meet our maximum error requirements. And so you're going to have PQ, and then it's Z divided by E, quantity squared. Probably a little easier to calculate than what I wrote down. And then I'm going to discuss this in just a moment. Okay, so Lombard Electronic Companies has just installed a new machine that makes a part that is used in clocks. The company wants to estimate the proportion of these parts produced by this machine that are defective. So that's what we're studying. If it's defective, we're counting it. The company manager wants the estimate to be within 0.02 of the population proportion with a 95% confidence level. What is the most conservative estimate of sample size that will limit the maximum error to within 0.02 of the population proportion? So let's write down everything that we know and that we learned as we read through. So we want the estimate error to be within 0.02. That's E. E is equal to 0.02. And then we want to be 95% confident. So 95% confidence interval. Notice we're solving for N. That's our question. Because we're dealing with proportion, okay, whenever we deal with proportion, we're going to be dealing with Z, okay? Now, our confidence coefficient is equal to 0.95, and I know that because we're looking for a 95% confidence interval. If my confidence coefficient is 0.95, that tells me my alpha is equal to 0.05 because my alpha plus my confidence coefficient must equal 1. Because I'm dealing with a confidence interval, half of alpha goes in the left tail, half of alpha goes in the right-hand tail. So that means I need to look up half of alpha to know my critical value. Okay, so I know what my z is going to be equaling. So I have my curve. I put mu in the very center, which is going to be 0 on the standard normal. I have 0.95, my confidence coefficient in here. I have half of alpha in here, 0.025. I have half of alpha in here at 0.025, and I need to know what is my z value that corresponds to this picture. Well, the easiest way using our current UWF tables is just to look up this right here, which is 0.025. Yes, it'll give us our negative z, but that's okay. I know how to deal with that. Okay, so we're just going to look up our z right here and here, and we're going to look up 0.025. So 0.025 is right here. 0.025, the area under the curve. This is the left-hand tail because this is what our table here shows. We come in here and we find 0.025 right here. So our value is negative 1.96. So it's negative 1.96. So we know that we want to be 95% confident of our results. So we're going to have a negative z, which is negative 1.96, and then positive 1.96. Z is equal to 1.96. Now remember, n is equal to, our formula up here, it's z squared, or just z, 1.96, divided by our e, 0.02, all of that squared, multiplied by p, multiplied by q. We haven't discussed what our p and our q are, right? We've got to mind our p's and q's. When we look through this whole problem right here, you're going to notice that nowhere did it give us even an estimate for what the proportion of defective parts is. We have no idea. It doesn't tell us. So when we have no idea and nothing to start with, the worst case scenario is we let P equal 0.5, therefore Q is equal to 0.5. That is the worst case scenario. It gives us the largest sample size that will meet these requirements. Okay, so in here, because we have no prior knowledge, we're going to put 0.5, 0.5. We're going to grab our calculator. Turn it on, and then put it in. So this is going to be parentheses 1.96 divided by 0.02, close parentheses, square it. Okay, so that took care of this part. Now I have to multiply it by 0.5, so times 0.5, that's my P, times 0.5, that's my Q, hit enter. So 2004, we have to sample 2004 parts. In this case, 2004 parts in order to be assured that we are 95% confident that we will be within 0.02 of the population proportion. Okay, it's a lot of parts, so that's when it comes back to how cost effective is it to determine that we need to be 95% confident. Maybe if we were only 90% confident, it would make it more cost effective. On the other hand, maybe it's no big deal to grab 2,401 parts. That's all going to be determined by management. Alrighty, so again, if you don't have a P and Q provided in your problem, the worst case scenario is going to be that you allow P equal to 0.5. And that is exactly what your formula sheet right here says. Right here, it says without an estimate for P, use P is equal to 0.45, or 0.5 rather. So make sure that maybe you put a little note here that says no P provided, use 0.5 or something. Just make sure you know what that means, okay? Well, thank you so much for joining me. Time on Thursday mornings, Tuesday, Thursday mornings has been very productive and terrific. If you're not attending, you're really missing out. If you've made it this far into the video, I would like you to send me the code word Star Wars, and then I know that you made it all the way through. That was our first code word for this particular video, and I'm looking forward to hearing Star Wars from all of my students. Feel free to just send me a text, and remember, it doesn't matter what time of day or night that you send me that text, because I always keep my sounds off. You will not bother me. Join us Thursday morning, and we'll practice a lot of these concepts, and you have a good night.